So we've talked about how to use enthalpy for a reaction if it's given to us. We also know now, using calorimetry, how to measure the enthalpy change for a reaction, whether that's using constant pressure calorimetry or bomb calorimeter. But what if we have a reaction that's not easily measured directly, that we can't just do constant pressure or bomb calorimetry on? And what if we want to know the enthalpy change for that reaction? So if I have this generic reaction, A plus B goes to C, but I can't measure it directly, how do I determine the change in enthalpy? We can do this by taking advantage of something that's known as Hess's Law. Hess's Law states that the net change in enthalpy for a reaction is equal to the sum of the changes of enthalpy for individual reactions that sum to that net reaction. Now, what does that mean? How does that work? The fundamental principle here is that anything that you do to a mathematical equation, you can do to a chemical equation. So you can add multiple chemical reactions together, just like you would add mathematical equations. So A plus B goes to W plus X, and you know the enthalpy change for that reaction. And you have another equation, W plus X goes to C, you know the enthalpy change for that reaction. Well, you can simply add those together, and you would add everything on the left side of the equation. So you get A plus B plus W plus X goes to W plus X plus C. Then you just go through and you cancel out anything that appears on both sides of the equation. So W appears on both sides, X appears on both sides. You cancel those out, and you're left with a net reaction, which is just A plus B goes to C. Just as you add the chemical symbols, you will also add the enthalpies. So the net enthalpy for this reaction is, according to Hess's law, is just the sum of the enthalpies of the individual reactions. So it's just negative 101.2 plus 20.3, and we come out with negative 80.9 kilojoules as being the enthalpy of reaction for this generic reaction that we were not able to directly measure using calorimetry. And you can see that Hess's law is a very powerful tool. It allows us to get quantitative information about the amount of heat required or given off for reactions that we may not be able to directly measure, or that perhaps it might be time-consuming or costly to measure, and we already have the values for individual reactions that we could sum up to get to the net reaction. Now, as I mentioned, anything that you do to a mathematical equation, you can do to a chemical equation. So if you want to multiply everything by some number or divide everything by some number, you can do that. And we'll go through a couple more examples. So another generic example, say we want to get A plus B goes to C, and we've got two equations. A plus Y goes to W plus X, and we've also got C plus Y goes to W plus X plus B. We know the enthalpies for both of those reactions. Well, I can't just sum up those reactions as they're written right now, because I would have A plus Y plus C plus Y, so I guess it would be A plus 2Y plus C on the reactant side, but that doesn't match with the net reaction that I want. What I need is A on the left side of the equation, and I need B on the left side of the equation. And currently, B is on the right side of the second reaction. This is where that concept that we mentioned earlier for enthalpy, where the enthalpy of the reverse reaction is the same in magnitude, but it's simply opposite in sign of the enthalpy of the forward reaction. What that means is we can write a reaction in reverse and simply change the sign of the enthalpy if we know the enthalpy for it written in one direction. That would be useful here because we would like to reverse the second equation so that I get B on the reactant side rather than being on the product side. So if I do that, if I simply reverse equation 2, then what I need to do is I need to change the sign of the enthalpy. It's equal in magnitude, but simply now, rather than being absorbed, it's being given off. And so the sign changes from positive to negative. Now, if I sum up those equations, I'll have A plus Y plus W plus X plus B on the left side, and W plus X plus C plus Y on the product side, well, W, X, and Y will all cancel out, and I will be left simply with A plus B goes to C. And now I can simply sum up those enthalpies, 251.0 plus negative 122.3, and I'll come out with the enthalpy for my net reaction as positive 128.7 kilojoules. So you can see that I'm able to reverse reactions as need be. Let's go through another example. So a third generic example here. 2A plus B goes to 3C. We don't know the enthalpy for that reaction. That's what we want. What we do know, though, is three different constituent equations. One where A goes to 2X, one where 4Y goes to B and 4X, and one where 2Y goes to 3/2 C. And I've got corresponding enthalpies for each of those. If I were to simply add those equations as they are right now, I will not get the appropriate, I won't get the appropriate amounts. For one thing, I'll notice that I need 2A in the final net equation, but in the only equation that has A in it, I only have 1A. So I'm going to have to do something to that equation. B, if I look at that, I can see that I only have one of them. That's good, that's all that I need, but it's on the wrong side of the equation. So I'm going to have to do something with that equation too. And then for that last equation, well, I have C, but I don't have the right amounts of it. I have 3/2 C, what I need is 3C. So when you're trying to figure out how to manipulate the individual reactions to be able to sum up to the net reaction, what you want to do is look at each individual piece and preferably choose pieces that appear in only one equation. Start there first, and then work to the other species, and only pay attention really to the species that appear in the final net reaction, or pay most attention to those. So here, when I look at this first, I can see that I need 2A, but I only have 1A. Now it's on the right, it's on the correct side of the equation, but there's only one of them. So I'm going to have to multiply that equation by 2. And I'll multiply everything in it, including the enthalpy, because enthalpy is an extensive property. So the amount of it matters. If I multiply the equation by 2, I multiply the enthalpy by 2. Second equation, I have the right amount of B, but it's on the wrong side. So I'm going to have to reverse this equation, and that will reverse my sign. Third equation, I have C on the correct side, but not the right amount. I'll need to multiply by 2 to get me with 3C. That will also multiply my enthalpy by 2. So multiply equation 1 by 2, reverse equation 2, and multiply equation 3 by 2. If I do that, that changes equation 1 and changes the enthalpy. For equation 2, it simply changes the sign of the enthalpy, and for equation 3, that changes the magnitude of the enthalpy. I add all of those together now. I have 2A plus B plus 4X plus 4Y. But then on the product side, I have 4X plus 4Y plus 4C. Well, the 4X's cancel because they're on opposite sides. The 4Y's cancel because they're on opposite sides. And I'm left just with the desired equation. 2A plus B goes to 3C. And I can simply sum now my enthalpy values. And I come out with negative 29.7 kilojoules. Okay, we've done several generic examples. Let's do an actual example using chemical reactions. So what is the enthalpy of reaction for the incomplete combustion of solid carbon to form carbon monoxide? This is not an easy reaction to measure the enthalpy for, because when you try to do combustion of carbon with oxygen, you're mostly going to get carbon dioxide, not carbon monoxide. So this isn't one that's easy to measure directly. But we have two equations that are helpful. One is the complete combustion of carbon to carbon dioxide. And then we also have, if we've got carbon monoxide, we can do a second combustion reaction with that to form carbon dioxide. And those two equations have their corresponding enthalpies, and I can use these now to help me determine the net equation and the net enthalpy. First thing I do is just evaluate what I have present in the net equation and where that appears in the individual equations. So carbon appears in the net equation and only appears in equation 1. I can see that I need 2 of them, but I only have 1 in equation 1. So I'm going to have to multiply equation 1 by 2. Then I notice that I also have CO. Now, oxygen appears in all 3 equations, so I don't really want to try to balance. I don't really want to try to figure that one out because it appears in multiple equations. I'd rather start with the species that appear only in 1 equation, other than the net equation. So CO appears in the net equation and then only appears in equation 2. Now it's on the wrong side. It does have the right number of them, so all I have to do is reverse equation 2. I have to multiply equation 1 by 2 and reverse equation 2. If I do that, I come out with now negative 787.0 kilojoules for equation 1 because I also multiplied the enthalpy. And now change the sign of the enthalpy for the second equation because I reversed it. If I sum this up, I'll have 2C plus 2O2 plus 2CO2 on the left side, and then 2CO2 plus 2CO plus O2 on the right side. The CO2s cancel. Now I have 2 O2 on the left and just 1 O2 on the right. Well, I can cancel one of the O2s then. And so then I'm left with just 1 O2 on the left. So then I end up with my net equation. I sum the individual enthalpies here, and I come out with the final enthalpy for this reaction, which would be difficult to measure, but I can calculate from reactions that are easier to measure. Okay, so let's do one kind of group problem on that. You can pause the video now if you want and try to work on this on your own, but I'll carry through and work through the problem. So we are given 3 constituent reactions, and we're asked to calculate the change in enthalpy for the reaction of ethylene with fluorine gas, and we're given that equation here. So the first thing to do with this reaction is look at the net reaction and identify the species that appear in only one of the constituent reactions, and then we'll try to adjust the constituent reactions from there. So if I look at C2H4, this very first one here, I notice that it appears only in equation 3. And I have the right amount, but I don't have it on the right side of the equation. It's on the wrong side of the equation. So I'm going to have to reverse equation 3. Now, if I look at F2, shown here, F2 appears in equation 1 and equation 2. I probably don't want to touch that one yet. But let's look at one of the other ones. How about CF4 here? It appears only in the net equation and in equation 2. It's on the right side of the equation, but there's not the right number of it. So I need to multiply that by 2 to get the right number. HF appears only in equation 1. And again, it's on the right side of the equation, but not enough of it. So I need to multiply equation 1 by 2. If I do this and then write this all out and sum these up, I should be able to get the remaining species should all balance and cancel out. So if I write equation 1 multiplied by 2, I would have 2H2 plus 2F2 goes to 4HF, and my delta H is now whatever, negative 537. 537 times 2, this is negative 1074 kilojoules. Equation 2, I'll have 2 carbon plus 4 F2 goes to 2 CF4. Delta H for this is now negative whatever 680 times 2 is. That's 1,360. 1,360 kilojoules. And then I will have equation 3 written in reverse. So C2H4 going to 2C plus 2H2. And delta H for this is now negative 52.3 kilojoules. If I sum all of these up, what I end up with, if I write it all out, I will have 2H2 plus 2F2 plus 2C plus 4F2. So what we can do here is actually combine those together. So 4F2 with the 2F2, I'll just make that 6F2 plus C2H4. Now on the product side, we have 4HF plus 2CF4 plus 2C plus 2H2. If I look at this, I can cancel out the 2H2 with the 2H2 on this side, the two carbons on this side, and I'm left with the net equation that I want. 6F2 plus C2H4, that's what I want, goes to 4HF plus 2CF4. That's the net equation that I want. And I sum up the individual enthalpies, and what I come out with then is, for this reaction, I should have negative 1,074 plus negative 1,360 plus negative 52.3, and I should come out with a large number here. I follow the significant figure rules for addition and subtraction, so I'm limited by the least number of decimal places, and I come out with negative 2,486 kilojoules for this reaction. And that's how we use Hess's law to help us determine the enthalpy for a reaction that would be difficult for us to determine otherwise.